All right, Dave, it's your turn. Tell us what you've been up to at Geoscience Australia.
Okay, thanks, Helen. And I'll try and find my, oh, there it is. And hopefully people can see. Oops, I better start at the start. No, that's the wrong presentation. Just a minute, I'll have to go and find.
No problem.
I was going to say, that one looked very familiar to me.
Yeah. No, I was actually changing stuff from it. Okay, this is the one. Right.
You're like me, Dave. Keep working on the presentation right up until the 30 seconds before you give it.
Yeah. This is the proper one. Okay,
Excellent.
I will share the screen now, and this should be right. Okay.
That looks like it.
Yep. Okay. Okay, so you should all be able to see that. So I'm going to talk about
you just need to switch the screens.
Oh, okay. I don't know. Okay, does that work now?
Yep, that's perfect.
Okay, great. Okay, so I'm going to talk about the research that we've been doing in Geoscience Australia, and also going to mention some of the research that you guys at GSQ have been doing, and also an overview of what some CMMI has done. Al's already talked a little bit about it. I'll fill in a little bit of information. Now, I'm talking on the behalf of many people, and I really want to emphasize how many people this includes, okay? And it includes people, obviously, from Geoscience Australia, both present staff and former staff, but also we've got people from the Geological Survey of Canada. We've heard from Louise and Chris about that, and then United States Geological Survey from Al, and there's a lot of other people being involved. But I'd like to point out that there are others involved. Initially, Vlad has had a very large role in the CMMI, and also Matt Valetich has actually been doing some really good work, and I'll mention a little bit about that. We've also had some collaboration with a bunch of people from universities in Melbourne, and they've actually had influence in what we're talking about, and we've had previous collaboration with Carl Brauhart from the University of Western Australia. So there's a lot of people involved in this. I counted up the numbers, and there's 49, and I probably missed one or two. So there's probably over 50 people who've been involved in the work that we've been doing in the last few years. So I'm going to start out on some of the early stuff that we did, and we started looking this in about 2012, and it was a project by Roger Sciro, and I think it was provoked by the rare earth element bubble that we had in 2011. And so anyway, we actually had a project looking at critical commodities in a high-tech world. And the report, you see the cover of the report there, but I've also shown a diagram from that report, which just illustrates some of the geological information which is incorporated in that report. And what we have here is a cross-section of a convergent margin, and indicating what types of mineral deposits might be occurring in the back arc basin. And so we've got VHMS, obviously, but we've also indicated what other byproducts or other commodities might be present in there. And we actually identified a number of critical commodities, and those are actually underlined in these diagrams. There's a whole series of diagrams that you can actually go back and look at what at the time we thought would be present in that particular mineral system or those deposit types. So we've been thinking about this for quite a while, and this actually, this work actually started us out on a couple of other projects, and we'll just show some of that now. And the first one was potash. Now, in Australia, potash is seen as a critical commodity. We don't produce any At present, we import it, a lot of it, partly from Canada, from Saskatchewan, but it's a critical mineral because our farmers actually really need it. And so we'd like to have an indigenous supply. And so we had a project looking at potash in salt lakes. Okay, and this is a map, and it's a mineral systems approach. And they actually identified a number of regions in Australia that we thought had salt lakes with potential for potash. And there, you can see the report, the cover of the report, and it was headed by Terry Murdoch, included a lot of people at GA. And one of the areas that they focused on is in northeastern Western Australia, where we have a number of salt lakes, Lake Wells and Lake Way. And they actually mapped and they identified number areas of high potential. And you can see Lake Way and Lake Wells as being some of those areas. And this was put out in, as I say, in 2013. And what happened is we released it in 2013. In 2015, we had a company inquire about the potential for potash. And in August that year, they actually went in and they actually looked at one of the lake wells for its potash potential. They found stuff, and then they shifted late in that year, they shifted their focus to potash. So, and they actually changed their name in early 2016. So they're now called Australian Potash. And then they identified a scoping study that indicated the potential for a low-cost potash operation. And this is all due to the GA work that was done in 2012. And we're anticipating having a mining, or actually extracting and evaporating of the brine starting in 2023. And you can see a photograph, an aerial photograph of the operation as it was relatively recently. Now, at GA, we actually try and justify the sort of things that we're doing by looking at the net value or the net benefit in terms of the money we've spent. And so we've actually had a external consultant at Allen Consulting look at this for us, and they did their analysis, and they reckoned that about $200 per dollar spent by GA will come in net worth for Australia. And in terms of the Commonwealth government, i.e. taxations, we're looking at somewhere between $65 to $93 per dollar spent by Geoscience Australia. So this competitive work that's being done by us, it's being done by the Canadians, it's being done by the Americans, actually has value in terms of the economies of the respective countries. The next thing I'm going to give as an example is national scale nickel and platinum group mineral perspective map. Chris showed you what they've done in Canada. We've also done the same sort of thing, and it was released in 2016 as a GA record, and we actually used the GA sort of method of mineral systems method of identifying theoretical criteria, mappable criteria, and then weight data sets to come up with maps, and then combining them. And you can see in the far right-hand side, the final result. And there's actually, and hopefully you can see that, there's in my arrow here, you can see a little red dot here. That was actually picked up by a company called Chalice Mines or Chalice Minerals, and they actually started to look at it. So we started the mineral potential mapping project in 2012. We published results in 2016, and Chalice Gold Mines took up tenements in that red area in 2018, and they put their first drill hole into the Julimar project, which identified copper, cobalt, nickel, palladium, and other platinum group elements in 2020, and they've gone on since then. They were going to release a JORC resource, I think, in mid this year, but they've actually pushed that back because they've continue to get good intersections from it. And so they're going to actually release the JORC compliant resources probably at the end of the year. This is a major discovery, which we think can be directly attributed to the work that we did on the nickel potential map. Hopefully, Chris's map will generate the same sort of thing. It just has the same potential. But again, if we look at the value to Australia, and this has a lot greater uncertainties because we don't know how big Julimar is, but you're looking at somewhere in the hundreds of dollars per dollar spent in terms of gross wealth to the country, but also in terms of taxation, you're looking at about $100 per dollar spent. Now, if you actually sum up the taxes, the Julimar and the Salt Lake project, actually the sum is about the same sort of money that we spent, that we're spending as part of the EFTF program. So we're actually paying for ourselves. Okay, now I'm going to move on to the next aspect, and this is the critical mineral mapping initiative. And as has been already stated, it's a joint research initiative between GSC, GA, and the USGS. It formally began in 2019. And as we know, it can involve other research organizations, and we'd like to encourage that. And the best example is the work that Vlad has been doing with us from the GSC. Now we have two major projects. The first one is the critical minerals and ores, and Al has talked about the systems classification. We also have another project run by Doug Kreiner from the USGS, looking at a tectonic classification of mineral deposits. That's taking the systems classification and looking at in a tectonic framework. And the other thing which I've sort of been leading kind of is the ore geochemistry, and that's getting actually the database together and a portal release. The other thing that's been happening, and Chris talked a bit about this, was mineral potential mapping. And we're looking specifically at basin hosted mineral systems. And Mike Gadd at the GSC has been leading this with Chris Lawley. So here's the CMMI portal. It's the first draft of it, and Al showed a version of this. And this just indicates the location of the deposits that we have data from, and also the different colors indicate the deposit environment classification according to Al. Now, the intended release date is the 30th of June, 2021. Unfortunately, we are having some delays. We have a few I's to dot and T's to crosses, but we're doing that. The second thing is it's global in scope. So you can see there's a lot of data from North America, and that image that Al showed before showed the database from Australia, but we also have data from Europe, South America, Africa, pretty much around the world, although there are some areas where we have a lot more, a higher density of data. Now, it's the published data that we've been able to acquire, and also data from the GA, the GSC, and the USGS geochemical data bases. So that for Australia, that would be Osman. It's been classified according to the classification that Al just talked about. The thing is that we've included as much of the periodic table as possible. Okay, so we tried to get everything analyzed, not entirely, but we've done pretty well. But the important thing is that it also includes analytical data, analytical metadata, i.e. how the sample was dissolved, how it was analyzed, the detection limits, and a whole bunch of things like that. The last thing is going to be updated semi-annually. So as I say, sometime before June 30th, we'll have the initial portal put up, but then we'll try and update that by the end of this calendar year again with some additional data. And so if anybody has any additional data that they want to put in, that'd be great. Okay, so now actually talk about how we might use this data. Okay, and Al started to talking about predicting critical minerals and ores. And I've just shown a diagram from Gavin Mudd and Tim Warner. It's an unpublished diagram, just looking at the relationship between molybdenum and rhenium. As we know, molybdenite is quite commonly a host rock for rhenium. And there's actually a quite strong correlation between rhenium and moly and many individual mineral deposits. And you can see the different lines that Gavin and Tim have indicated. But the other thing is that, and there's work that's been done partly for rhenium osmium dating of mineral deposits, but we know that the rhenium molybdenum ratio actually depends quite strongly on the type of deposit. For example, deposits with intermediate magmas, porphyry copper deposits tend to have higher rhenium to moly ratios than deposits associated with felsic magmas, such as porphyry moly deposits, which have much lower rhenium to moly deposits. So we can actually use that information and the deposit classification that Al and the rest of us have been putting together to predict the rhenium concentrations in the moly and the copper moly ores and other ore types. So that's an idea of kind of what we can use, but as an example, we'll actually go to germanium. Germanium is a minor, but it's a critical element. It's used in fiber optics, such as a semiconductor and as a polymer catalyst. The production increased more than doubled from 2000 to 2019. Currently, well, at least in 2019, China is the dominant producer. It produced about 65% or 85 tons of the stuff in 2019. Now, the important thing is a lot of that actually doesn't come from mine production. It actually comes from the fact that there are smelters in China which actually recover the germanium. There's also smelters in Belgium which recover the germanium. There are other smelters which don't recover germanium. So it's actually not necessarily a mining issue, it's actually a smelting issue. The other thing is the Australian grades and resources are not publicly known. So we're going to actually try and have some guesstimates of what those grades and the amount of germanium that might be present using the geochemical data set that we've got. And this is just a start. It's using only a small proportion of that data set, but here's some of the examples. Okay, so what we've done is we've actually looked at a number of different zinc deposits, because zinc deposits are the main source of germanium. And we've looked at sediment-hosted deposits, both siliciclastic carbonate or HYC Mount Isa-like. We also looked at sediment-hosted deposits, siliciclastic mafic, which would be more your Broken Hill type deposits, and then your volcanic-hosted massive sulfide deposits. And you can see that the siliciclastic carbonate, Mount Isa or HYC, actually contains significantly more germanium on average than the other types of deposit, which actually tells us something. Okay, and you can see there's a very broad correlation, not perfect correlation, but we can actually start to use that information to actually make some predictions. Okay, so what we can do is we can actually take that ratio that we've calculated for each, or that the median value for each of those deposits, and actually make an estimate of the germanium content of the zinc deposits. And from this, you can actually see there's some. It's quite striking how the North Australian zinc belt, HYC, Mount Isa, etc., actually is a very significant potential germanium resource. And it's actually, the other interesting thing is that you can actually understand that in terms of geochemistry. So we think that those deposits form from relatively low temperatures, fairly saline deposits that are very, very oxidized. And so if you take such a fluid and you reduce it, you will actually get into the germanium, you will actually precipitate out germanium. And that's probably why these deposits are so enriched in germanium. If you look at the Mississippi Valley type deposits, they're all also enriched in germanium. And in fact, there's a MVT deposit in China, which actually quotes a germanium resource. So we've actually done the same sort of things for other critical minerals, and one of the main things that we're interested in is the lithium pegmatites in Western Australia. But the important thing about those is that before they were lithium pegmatites, they were actually pegmatites which produced tantalum, tin, and in some cases niobium. So we've gone from the same pegmatites being a tantalum resource to being a lithium resource. And so the idea is, can you actually get back to the tantalum and the niobium and the tin contents using the same sort of procedures that we've actually developed? Because in many of these cases, the tantalum, niobium, and tin resources are not reported. It's just the lithium resources. So we think that we can actually do that, and we can actually make estimates of the amount of tantalum and niobium hosted within those lithium pegmatites. Again, it's important to stress that these things are very preliminary. They're not going to make a JORC compliant resource, but they're an indication of what's possible. And along the same lines, and I'm going to use some of Matt Valentich's work from the GSQ, he analyzed rare earth element potential in phosphites following the paper that Paul Emspo wrote. And so he actually looked at this, and he came up with a range of phosphites in the Georgina Basin. And you can see the range, which is normalized according to a shale, a Proterozoic shale. And you can see that the Georgina Basin phosphorites actually have a relatively flat rare earth element pattern, which means they're actually quite enriched relatively in the heavy rare earth elements. And those are the more valuable ones. And you just see the indication of the value that Matt's put onto this. And so what we did is we actually took some of his analyses and actually calculated the true value of those things, the in-ground value. And I think this was done in September. So those are the values that we used. And you can see that the value of the rare earth elements is $300 per ton. That's for one deposit. For Ardmore, which is a very small but high grade deposit. For Phosphate Hill, which is the main deposit in North Queensland, it's about $30 per ton. Now, when you take the fact that the price of phosphate rock is about $75 per ton, there's actually potentially a very significant resource of rare earth elements in these phosphate rocks. The difficulty is getting them out, okay? And that's some of the work that Rick talked about earlier and Helen talked about earlier in terms of developing metallurgical techniques to getting them out. So there's a key here, but you can see the potential. So if you look at just the potential value for the Ardmore deposit for high grade, it's about $330 per ton, much greater than the value of the phosphate rock. And the same thing applies to Phosphate Hill. It's still significant. It's about half the value within the rare earth element resources. And so we can actually look at this, and this is some diagram that Yevgeny Bastrikov's been developing. It's a radar diagram looking at critical minerals or a range of minerals or elements, both in terms of crustal normalized, so a crustal value of 1, that circle, this circle here is a value of 1, so it's not depleted, it's just sort of normal crustal values, but you can see that all of the rare earth elements are actually quite strongly enriched relative to crustal values. But the other thing that we've done is that we've actually taken the value, the dollars value of these things, and you can see that the value is actually quite strongly dependent on which particular element you're looking at. For instance, neodymium, dysprosium are the main value that you see in both Ardmore and Phosphate Hill. And so looking more in the economics, we've actually put this into our economic fairways mapper. And so this is what we've done. So we've done, so what this mapper does is it uses grade and tonnage information combined with infrastructure and mining costs to actually estimate the break-even value of a resource. Okay, it includes the cost of development and resources, and it calculates this. And so the white values, or near white, are actually near break even. The blue values are what you lose money on, and the reds and shades of pink are you'll make money. So it's quite interesting that when you include only the phosphate value, okay, and this is the resource for Phosphate Hill, and Phosphate Hill is somewhere around in here. It actually illustrates that it actually works. This thing has a positive net present value, and therefore is a mine. It is a mine, and so the model seems to work. But if we actually add in the rare earth elements, it changes things quite dramatically. It becomes much more economically viable. Now, unfortunately, we don't have the cost values, the exact cost values in terms of what it would take to produce the rare earth elements, but we have used another model from a different deposit to estimate. So these are sorts of an idea of possibly what might be possible. So again, we're looking at possibilities, and the resource potential of rare earth elements and phosphate is actually quite a significant potential in Queensland. So in summary, we at Geoscience of Australia have identified exploration targets, including critical minerals, as part of a national scale mineral potential analysis, both in phosphates and nickel. This has directly or indirectly resulted in the discovery of significant mineral deposits and new mineral provinces. The Julimar deposit is within a new mineral province. The economic modeling suggests that there's significant returns on investment, both in terms of wealth created and in Commonwealth taxation. So we can tell to our economics departments that we actually are value for money. We've entered in a joint initiative with the GSC and the USGS and the GSQ to undertake a number of potential projects to identify potential for critical minerals. The aspect that I talked about was using the data that we're generating or publicizing to predict and understand the geochemical and geological controls on critical mineral concentrations in ores. And finally, and I'd like to really stress this, we actually geologically probably know more than we think we know about critical minerals and ores and where we might find them. A lot of the issues with critical minerals actually relate to economic issues, i.e. small markets or monopolies or metallurgical issues. And so they're going to be much more important to include that kind of information in the studies that we continue on in the future. So that's it for me, and I'm ready for questions. So I will stop sharing my screen. Right.
Thanks, Dave. It's almost 12 o'clock, so it might be almost beer time as well. That's really good. So I know as you've been talking, I've had Matt Valetich on the Teams Messenger asking me questions about what was Dave saying, and so he's very keen, as always, to see how that work progresses, and really glad that GA have taken some of that initial work that we did and run with it to such good effect. So
well, I think what Matt's done is really excellent, and what you guys are doing are really excellent too.
And it builds on a lot of the work that, as we said before, Paul Emsbo at USGS has done, and so that's really good. Yeah. A global problem-solving team.